Hi everyone, we continue to explore our database tool. In the previous episode, we looked at how the Insert Record button on the user interface works for us. Today, we'll look at the Insert Record function on the programming level. Now, let's log into the program as an admin and display a table from the database, the structure FAB table. I will now enter data here. In this case, it is a staff structure, but I will enter random data since right now we are interested only in the principle of how it works. And let's see how this function works. So we refresh the table by adding a new row. Now let's see how this works on the programming level. Yes, but before that, let's talk about the devices that you see in my background and why they're here. Right now, I'm holding a device called NI USB 6008. This is a multifunctional device. We're not going to look at all of its capabilities right now. We're interested in only one of its functions. And here is the second device. This is a photosensor. With it, we can determine the level of illumination in volts. In other words, the light that hits the photosensor is converted into a photoemission current, which in turn opens a transistor, and as a result, the voltage between the collector and the emitter changes. This is a very rough explanation. Don't be too strict with me. We are not studying physics right now, we are doing programming. So we'll measure this voltage through our USB device, which will somehow be connected to our program. And we'll not only measure this data, but also write it into our database. In this way, we'll turn our database into a real-time program that is connected to real external processes. And here, of course, we'll talk about object-oriented programming, what objects are, how they are understood by different developers, and we'll briefly touch on how they are used in text-based programming languages, what the main differences are, and the undeniable advantages of our program compared to text programming languages. But that will be a little later. For now, let's finish analyzing our insert record function and see how it works on the programming level. Now I go to the block diagram directly to the case that is controlled by the insert record function, button function. In the previous episode, we looked at the logic of how we get into the true case, how we get into the false case, and why we have the duplicate table, dbTable2, here. Now we'll look at the function that we ourselves invented and created so that our insert record operation would work. We designed it this way. There are many ways to do this, but I wanted it like this. Maybe someone might suggest a different logic. Please share your ideas in the comments. To me, it seems that this is the most optimal option. So our program starts running from left to right, as usual. We open the database, then we do list tables, then list columns, then we execute our task, display the updated table with the new values, and close the database. This is the standard routine that we do with the database. The only non-standard part is the task itself and the logic that we use to solve it. Even though our diagram may look complicated at first glance, let's try to understand the essence and see how simple it actually is. So the data from table 1, the future data, and the data from table 2, the current data, go into the function delete from array. With this function, we remove the rows that we just added, but those are actually the rows we need. So we take these removed rows and start sending them one by one to be written into the database. Here, as you can see, we have a for loop with the 1D array to string function, which we use to check whether we have something to write into the database. In other words, whether it is not empty. If it is not empty, then we go into the false case. How the function empty string path works, we discussed in previous episodes. We also see a new function here, array to v cluster. This function comes from the OpenG library, and where we got this library from, we also discussed in previous episodes. Thus, using this function from the database connectivity toolkit called dbtools insert data.
It inserts a new row into the table in the database identified by the connection reference.
So, by using this function, we insert our data into the database table row by row. We have data, connection reference, table, and columns. This means we have everything needed for this function to work. Let's place probes on each of these terminals and check if that is really the case. I put the first probe on the data, the second probe on the table, and the third probe on the columns. Now let's run the program and see what we get. Here I need to go again into my structure fab table and enter some data. So let's look at what we got. The first probe is data. Here we see a variant cluster. The data has arrived. The second probe, here we see our structure fab table. The data has arrived. And the third probe, we see a 1D array with our columns. We also see that the data has arrived. Well, this is actually obvious anyway, because we already displayed the values from our database on the screen. But this probe tool is very convenient when we do debugging, searching for an error. In this case, we have no errors. So we've looked at how the insert record function works. And now we'll move on to the next function, create table. But before that, as I promised, let's talk about what object-oriented programming is. There is still no consensus on what objects in programming actually are and what the term OOP means in general. Opinions are very different. Let's look at it by analogy. Today, as they say, more than 1 trillion lines of code have been written. In our galaxy, for example, there are fewer stars than that by an order of magnitude. We can assume that every line of code has some meaning, and if we start searching for the meaning in every single line, we simply won't have enough lifetime to find anything. For example, we know that to count to 1 billion without eating, sleeping, just counting, it would take us about 100 years. So the question is, do we really need to dive into every tiny detail? Especially considering that every detail can be interpreted differently, because how many people there are, that many interpretations there will be. One person describes a process one way, another person uses completely different words. And in general, if you watch one respected blogger, then another one, and another one, you'll just end up with a complete mess in your head. Alright, let's not overthink it, let's just describe everything in our own words. So I have an object in my hands, in this case a photosensor and a microcontroller, and I need to reproduce a clone of this object in my program, which will also have inputs and outputs. In other words, on the software level, this will be a simulation in the virtual world of our object from the real world. This means the object must have an input where something comes in and an output where we understand what is coming out. First, let's determine how our computer sees this object. For this, I have a tool called MAX, Measurement and Automation Explorer. Now I plug the USB port into our device and connect it to the computer. What do we see in Max? What changes happened? Here is our device connected, NI USB 6008. Here it is disconnected and here it is connected again. We can see whether the device is connected or not. We can also check it in Windows because this is a PNP, plug-and-play device. We'll also talk about DAC drivers, digital acquisition devices, later. Here we have the DAC drivers installed. We'll talk about how to install them later as well. In Windows, through the control panel, we can also see this device. Here it is, and it has some properties, but to see more details, we'll use our tool Max. So we see our virtual object, or rather the virtual clone of our real object. What do we see here? On the Analog Input tab, we have options for connecting to different terminals. In this case, we're set to Analog Input 0. That's exactly what we need. What modes do we have? There are several modes, but we are interested in continuous acquisition. And here the input configuration is suggested as differential, but we need RSE. Differential means we use two inputs, for example, 2 and 1, with different potentials. In our case, we need RSE because we have a signal and ground. We'll set the maximum voltage to 12 volts. We'll leave the rate at 1000 Hz, 1 kHz, because high precision is not too important for us right now. Speed is more important. We'll set samples to read to 100. Let's run the program. Oops. Let's pause here and take a closer look. And here we encounter the first problem on the path from the real world to the virtual world. If you exist only in the virtual world, you can ignore the laws of physics. You can fly at the speed of light, move mountains, teleport, and defeat a pack of tigers. In the real world, there are limitations. And this is not only about the laws of physics. Very often it's simply about the specifications of the equipment you're using. For our USB device, there is a limitation on the input voltage for the analog input, and that limit is 10 volts. Of course, as users, we are protected from making mistakes both by the USB device manufacturer and by the driver itself. Let's see what the maximum voltage from my sensor can be. I disconnect BNC connector from the photosensor, take out the battery, and check what maximum voltage can be applied from my photosensor. Why do I know that a higher voltage can't happen? Because if the maximum voltage of the battery is, for example, 12 volts, then there is simply nowhere for a higher voltage to come from. So 12 volts is the max. And of course it can be less. Yes, I see that the battery is 12 volts. At the same time, we know that our USB device can accept up to 10 volts maximum. Technically, we should not use our photosensor directly because it can damage our USB device. But we'll take the risk anyway because I know that microcontroller manufacturers usually build in some voltage margin. But what do we do with the program that limits us on the other side? In this case, we'll have to outsmart it. I'll set the maximum voltage from our photosensor to 10, even though I know it can be 12. Let's see what error the program gives us. Requested value is not a supported value for this property. Well, that's exactly what I was saying. The requested value is 12 volts, while the maximum allowed is 10. Okay, I already changed it to 10. So let's outsmart the program at our own risk. I run the program. On the left side of our graph, you can see the voltage values from our photosensor. And right now, these fluctuations are between 1.3 and 1.4 volts. Let's call this white noise, something you cannot completely eliminate, something that is always present in our system as an imperfection. So fluctuations of about 0.1 volts. Let's remember that this is our white noise. I also have a red button on my photosensor, a battery test button. When I press this red button, the output of the photosensor simply shows the battery voltage. Now I press it and I see that the battery voltage is 10.6 volts. I press it again, 10.6 volts. So we verify that our virtual clone matches our real system, meaning there are no conflicts. And therefore, we can integrate our real-world object into our virtual environment. I press stop to stop the process. Here it's important to say that at this moment my system is occupied by the Max application. We may still need Max, but if I want to use this system from my database tool program, I need to free it from Max control. So I don't close Max, I just click on devices and interfaces, and in this way my system becomes available for further use. And since we might still need Max for debugging, I don't close it, I simply minimize it. So we checked that our system works and is ready to be integrated into our program. Now let's define the task, or as programmers say, let's create the architecture. What do we want? We want that when we press a certain button, we start recording data from our photosensor into the database. Alright, the task is set. Now let's break down what we'll need for this. We'll need a button. So I'll disable the power button and take this button here and place it right here. I will name this button Fetch Data and I'll rename it here as well. So our front panel is ready. We have a button that, when pressed, will start capturing data from the photosensor, and we also have a number that we'll use to create a table. Let's say that this number will be a part of the table name. We'll name the table, for example, fetch 1, 2, 3, 4, 5 with an underscore, and each sensor will have its own table and its own number. We'll use this photosensor as number 1, and the table will, with its data, will be called fetch 1. Oh yes, and why am I not using the number sign? Because when creating table names, we cannot use certain special characters. So, I want my subprogram to open in a separate window when it starts. To do this, I create a new sub-VI. Create new VI. I immediately go to the block diagram and look for anything related to DAC-MX. I click on any function just to get into the DAC-MX directory. Here we see many lower level functions. These are useful if we want to make working with our USB device more complex and access special capabilities. But today we're not going that deep. We'll create the highest level function or object. It won't have many options, but for our task it will be enough. The advantage is that it will be fast, almost instant, and already pre-formatted. So I select the DAC assist function, analog input. That means I'm making the same settings that we made earlier in the Max program. I choose analog input 0, maximum voltage 10 volts, terminal configuration RSE, acquisition mode, continuous samples. Samples to read 100 and rate 1 kHz, no changes. Let's also look at what other options we have in our virtual object. Not that many. For example, we can enable logging into a special file with the .tdms extension, which supports big data. But in this case, we'll not use this feature because we decided to write the data directly into the database. Alright, let's see how our system works. I press the run button and we see the familiar white noise. The sensor voltage fluctuating between 1.3 and 1.4 volts. I press the red button. This is the sensor test button, or you can also call it the battery voltage test button. And I see that the battery voltage on the sensor is also 10.6 volts. So we have configured our system. Now let's integrate all of this into the logic. Here the system immediately suggests creating a loop for the DAC assistant, automatically building a VI. I don't need that, I'll do it myself, although you can use it if you want. So I need to place the DAC assistant inside the while loop. And this while loop will run continuously at a speed of 100 milliseconds. I set it here, since high speed is not too important for us in this case. And I should say here that Windows limits the speed of our operations. I won't go deep into the details, let's just accept that the average delay will be about 10 milliseconds. This is because our command passes through Windows services that routed to the processor along the required path. So if we want to work in true real time, this system will not be suitable for us, and we would need to use other methods that exist in our program. For example, real-time applications and various systems like PXI or Rio. I keep getting distracted, the topic is very broad. I'll try to focus on our small local task. So we now have the object function that represents or simulates an object from the real world, and now we'll build the logic for it. On the front panel, I want to have a graph, and I also need a stop button. I go into NXG style and take a waveform chart, and I'll name it Fetch1 chart. I'll also need a stop button, which I'll take from the JKI Design Palette library. I'll use this one. I chose this style, but you can choose any style you like. We covered how to do that in previous episodes. Now we connect our fetch data indicator to the DAC assistant. And the cancel button to stop, yes, right here. This is standard. So let's check how all of this works. I run the program and I should say that when we run the program, it's immediately compiled. You of course know what a compiler is. We translate our code, which is on the back end in C++, into hex code. That is a very simplified sequence of zeros and ones, the so-called machine code that our processor understands. I press the red button on the photo detector and we see our white noise. And we see the battery voltage. White noise, battery voltage. So that this voltage jumps on our graph don't annoy us, we'll now disable autoscale on the y-axis and set the voltage range from 0 to 12 volts on our graph. We'll make this state the default and save it. Yes, we haven't saved this new sub-VI yet, so I save it in our project folder under the name sub-VI DAC fetch 1. And now I need to make sure that this sub-VI is in my project. Alright, this sub-VI went into the general directory, so I need to move it into the sub-VI directory. There, we moved it and saved the project. Before we start working on the window design and properties, I should work on this LabVIEW a little more. I go to the block diagram, and if I right-click on the Duck Assistant, I can see the option to turn the graphical image into an icon. I choose View as Icon because this matches my icon style and I want to stay consistent with it. Next, I need to add a standard timeout. Why do we use that timeout? Because every operation should have a defined duration. In this case, it will be enough for me that the data from the sensor is captured within 5 seconds. This will be my timeout. To do this, I use the following logic. I use the tick count function and set a limit of 5000 milliseconds. That is 5 seconds. And I add an OR operator. I also connect the cancel button, so the logic becomes either 5 seconds pass or I press the cancel button, whichever happens first. Let's check how our timeout works. And to see what is happening inside, I can connect a probe. I place a probe here and run the program. So we place the probe and run the program. We see that it reaches 5000 and stops. That means our timeout works. Now we need to establish a connection between our LabVIEW and the main program. For this, we need to create global variables, and we'll need 3 of them. We already covered how to create them in previous episodes, but let's repeat it. I find global variable in the functions palette and add it to the block diagram. I add the stop button, and also from NXG style numeric control, I add 2 numeric controls. The first one, let's name fetch 1 value, and the second one, fetch 1 index. Now, what else we need to do here? We need to set the data type for our numeric indicators. We know that fetch 1 value will be DBL and fetch 1 index will be I32. We check and set the representation. Here DBL, and here we change it to I32. Now I also need to save this, so I save it simply as global in the project folder. I'll name it global fetch. Okay. Then I move global fetch inside the project into the LabVIEW directory and save the project again. And now I close this, and here I need to connect the global variables: index, value, and stop. I connect index to the index, value to the data, and stop also to cancel. I can press cleanup, so everything is organized faster here. Now everything on the block diagram is ready, so let's do the final design. I need to reduce the window size a bit like this. Save, and then go into VI properties and set the size, set to current panel size, the one we just chose. We also need the window to be a pop-up. So in VI properties, customize, I disable everything except show run button, and I enable show front panel when called and close afterwards if originally closed. The rest we don't need. And also runtime position unchanged. Okay, design is done. Let's run the program. Yes, 5 seconds pass and everything works. Oh, I forgot to change the icon. I want to do that too. Just a second. I always forget this. Okay, done. So I run it again, press the button, 5 seconds. Let's check once more. I press the battery check button. Yes, everything works, and after 5 seconds the program stops. There we go. Well, let's also check whether everything really works. Here I have a flashlight on my phone. Let's test whether our photosensor actually reacts to light. Before that, let's make sure in what wavelength range our photodetector operates. On the back side of my photosensor, we can see the bandwidth range from 400 nanometers to 1000 nanometers. We know that in this electromagnetic spectrum we have visible light. And here the peak is indicated around 700 nanometers. That's closer to red. We also know that green is about 555 nanometers. Our phone flashlight produces white light. And we know that white light is a combination of different colors with a peak roughly in the same bandwidth range as our sensor. So it should work. Alright, I turned on the light and let's see. Here we go. We can see that when light hits the detector, the voltage increases. It increases, disappears, increases again. Maybe to make it more visible, I'll set the scale here to, let's say, 5. Let's run the program. We see that when light hits the detector, the voltage increases. And when the light disappears, the voltage decreases. Let's look again. Here I'm showing it again. Increases, decreases. We also have a 5-second limit set. Yes. In general, use cases of this program are not our main concern right now. By the way, it would be great to hear your ideas. Please share in the comments. Our task now is to write the data into the database. That is, when we press the buttons Fetch 1, Fetch 2, and Fetch 3, we will record one signal or another. And right now, when we press the Fetch number 1 button, we will record the state of our photosensor into the database, into the Fetch 1 table. But how we'll do this, I'll show you next time. And that's all I've got for today. Thank you for joining LaPlanta Tech. If you have any questions, please leave them in the comments. If you learned something new today, give this video a like and subscribe to learn more from upcoming episodes.